All right, so tonight we're going to start by covering maximum likelihood estimation and then go into the material on resampling. So to start off, maximum likelihood estimation. We're going to import some libraries that we're going to use first. Notice it always takes a while if I haven't opened a notebook in a while. All right, so we're going to start by just creating some fake data. So that's what's here. And then don't worry about the Z array. It's just so I can display the data in this way. But this shows what we have. So you could think of these as anything, like it could be from like a dice with this many sides. It could just be different possibilities, basically. So if we wanted to find the maximum likelihood estimation, we'd want to find a way to draw a probability curve that would maximize the individual probabilities. So basically draw a curve in a way that would contain most of these values and maximize their probabilities. So this is one way we could start by doing it. We could just take a random normal distribution. This one has a mu of 4 and a sigma of 1. And we can see how it kind of covers up most of the data points. And then we can basically take a PDF for each of these points and add them all together to get some kind of measurement on how well this fits. So if we do that, we get this value here, so kind of a low number. So now if we actually just put the mu as the mean of the data and the sigma as the standard deviation, and we plot that, we get this plot here. It seems to really cover most of the points. And then if we sum up all the PDFs for those values, we get a higher value. And so this would be what you call the maximum likelihood estimation for this data in particular. So when you talk about MLE, you also talk about MAP, which is maximum a posteriori estimation. Basically, MLE is a form of MAP when you have typically uniform distributions. So we're going to do some comparison now to kind of show you the difference between the two. MLE is basically the frequentist approach, whereas MAP is Bayesian. So consider flipping a coin 10 times. We get these results here. You can see we got more heads than tails. I'm not sure why I lost my slideshow here. All right, so we flipped these coins. What are the odds of heads? So the MLE approach to estimate the odds of heads for our coin would just be to take our sample data and add up all the heads and divide by the total number of flips that we did. So from this, we would get that the odds of heads is 60%. So the MAP approach would include our prior knowledge about the probability of most coins being 50%. And we're going to combine that with our observed sample data on the amount of heads we flipped there. So basically, one way you could think about it is that you would combine these two and basically average them. And you would get that our coin has a 55% chance of heads. So MAP combines prior knowledge and the observed knowledge. So another example, we roll the die 10 times and we get these results. So the MLE approach would be to sum the counts of all these different rolls divided by the total number of rolls and calculate the probabilities that way. But one thing you'll notice is for 3, we didn't roll any 3s in this small sample. So our calculated probability is 0. So that kind of shows like the downfalls of MLE. But then MAP, since it takes into account some prior knowledge about the probabilities, and factors that in, combining it with the observed data, then we still get a probability for rolling a 3, albeit like a smaller one. But basically, MAP is better when you have smaller sample sizes, and if you have a bunch of different possibilities, if you have like 50 or 100, there's a good chance in a small sample you're not going to get a representation of each one. So having some kind of prior probability to factor in can kind of help you get better probabilities in the end. So I know that was kind of a brief overview. I wanted to include some videos here to watch. Basically, the math behind MLE is very involved. You have to basically take multiple derivatives, you do log transformations, and basically there's a way, if we go back here to the beginning, so there's a way to prove that the maximum likelihood distribution function for basically normally distributed data is just equal to the normal distribution at that mean of the data and the standard deviation of the data. So if you watch, I believe it's the second video link here. Both of the videos are through StatQuest, which is a really good YouTube channel for statistic stuff, but he actually walks through step by step the math involved in the formulas. So I'd take a look at that if you're interested. And then there's also an article here that's kind of like an introduction to the topic, and it's a little less math heavy. So does anybody have any questions on this stuff?
Yeah.
Sorry, go ahead.
Oh, thank you. If there's any that is more used in certain applications than the other, because I don't see that on the MLE is going to be used for like large data sets, or I mean, or if there is any difference where you use one or the other.
So you can use MLE when you have like a uniform distribution. So if you have like a fair dice, but if there's any chance that the dice isn't fair, if it's slightly unfair in any way, then you would want to do an MAP approach. But basically, you would never really do these like on their own. They're kind of foundations for other parts of machine learning. So they're kind of just topics that you should at least be familiar with, even if you might not use them on their own.
Okay, thank you.
My questions are along the same lines.
Okay, so like use cases.
Yeah, and you said it's a foundation of other machine learning techniques. Do you have an example?
Actually, I do have another example. Let's see. Okay, so let's say that you have, okay, so a doctor wanted to run a study on people that have lupus and people who have a cold. And so he's done a study. He knows that with a certain set of symptoms, so if a patient has this set of symptoms, there's a 90% chance that they have lupus. And there is a 10% chance that they have a cold. So basically the MLE way and the frequentist way would be to look at this and say that if you have these symptoms, you almost certainly have lupus. What that fails to take into account is the prior probability of lupus and having a cold in general. So in general, we could say lupus is like 5 out of every 100,000. And having a cold is, I don't know, maybe 5 out of like 100. So the MAP or Bayesian approach would take into account these probabilities. And since the probability of having a cold is much larger than having lupus overall, then it's not really likely that you have lupus, given that you have these symptoms. So that's kind of another example to think about it in. Did you have any other questions or?
Yeah, I'm good for now.
Okay. It's a really heavy subject. I wish I could do it better justice getting into like the maths of it and maybe make it make more sense. But we will actually talk about it more when we get to machine learning, because then you use things like log likelihood and stuff like that. So we might revisit it later on. But if you do want to like dig into it some more, I would check out these resources if you can. All right, so with that done, we'll go ahead and move on to resampling. So if you want to open the resampling notebook. All right, so resampling. It's basically when we don't have enough data and we want to create more based on what we have. So the objectives for this part of the lesson will be, first we're going to dig into the NumPy library some more. I want you guys to be really comfortable using it, generating random data, creating sample data from distributions, and using it to resample data. And then in the second part, we're going to talk about two of the main resampling methods, the Bootstrap and the Jackknife methods. So first, we're going to do kind of like a code along. So this part isn't filled in. If you guys just want to type it in with me or just follow along on the screen, we'll import some libraries to begin. All right, so first of all, we just want to generate a random value from the standard normal distribution. So with NumPy, this is really easy. You just do np.random.normal, and that's all you need. You can run this a couple times. It's basically just a random value from a standard normal distribution. All right, so now we're going to generate 5 values from a standard normal distribution. So we set it up the same way. But then in the parentheses here, we pass in how many we want with the size attribute. So here we can choose 5, and that will give us 5 different values from the standard normal distribution. All right, now we're gonna generate 5 random values again, but this time from a normal distribution with a mean of 4 and a standard deviation of 2. So again, we kind of set it up the same way. p.random.normal. And this time we have to pass in that mean and the standard deviation. So the mean is given by LOC, basically like locale or location of the mean, however you want to think about it. So we'll pass in 4 there. And then the standard deviation is called scale. And you can pass in a 2. And then we want 5 values, so we do size equals 5. So there we have 5 random values from this specific normal distribution. And just let me know if I'm going through too fast through this. All right, so now we're going to generate 5 random values between 50 and 70 with equal probabilities. So for this, we're going to, it's all from np.random. But now instead of a normal distribution, since we want equal probabilities, we need to use a uniform distribution. So we'll do uniform, and then this takes 2 arguments, the low value and the high value. So the low would be 50, the high is 70, and then we want 5, so size equals 5. So there we have 5 random numbers between 50 and 70. So these have all been like decimal places, so maybe we just want integers. So to do random integers, we can just do .random, and then it's rand int. And again, you pass in low and high. So low equals 1, high equals 100, and size equals 5. So if you've noticed, when you do this multiple times in a row, you get different answers because it's random. But what if you're doing something that you want it to be replicable? You want someone else to do this using random, but still get the same random numbers. This is where the random seed comes in. So in the same cell that you're interested in keeping the same results, you can do numpy.random and then seed. And in here, you can pass in basically any integer value. So like I can do 47. Now, if I run this multiple times, the values don't change. They're locked in. So someone else with this notebook will get the same random values as you. And now if I change the seed, I get different values, but they stay the same as long as I've set the seed as the same value. So this really comes in handy later on. One application is when you're doing train test splits. So if you want somebody to reproduce your results, you want them to end up with the same split of train and test data, and this allows you to do that. All right, so now that's actually what we just saw. So just as a reminder, numpy.random.seed, and then pass in your value. But if you do this and then in the next cell, you put something, it won't use that seed. In Jupyter Notebook, it basically has to be in the exact same cell. All right, so now we want to pick 5 values from a list with replacement. So let's go ahead and make a list here. We'll just put in some like random numbers. All right, and then we want to pick 5 values at random from it with replacement. So we can do np.random.choice, and then we pass in our array, and then we tell it how many values we want. So we want 5. You'll notice it's with replacement, so we can get the same number multiple times. And now we'll do it without replacement. So it's kind of the same thing. We'll just use that same X array. So random choice, X. And now we have to, we still pass in, we want 5, but now we pass in replace equals false. So now each time we take one of the numbers out, it remains out from our choices. So the odds of the other choices in the box goes up. All right, so now let's say we don't want our choices from a box picked at the same probabilities. We want to give different weights to the probabilities. So we can do, let's first of all check how long our X was. So we have 9 items in that list. All right, so we do random choice. We pass in our array, how many values we want. And then we can pass in a probability array. So this has to be the same length as our X, and all the probabilities also have to sum to 1. So we could just put some in here. Let's see, that's 3, 4, 6, 7, 1, 2, 5, 8, 9, and 10. There we go. So now the first value in our array has a 10% probability of being picked. The second has a 20%, so on and so forth. So this way you could like simulate a loaded die or like a loaded coin. Lots of possibilities there. All right, and then last, we're just going to, let's see, or actually second to last, we're going to use our same X. So we're going to print that out first here. Notice the order, so 3, 4, 7, 4. But let's say we want to shuffle the order around and kind of randomize it. So we can do numpy.random shuffle, pass in X, and then we'll have to look at X again. And you can see that each time it just kind of moves them around at random. All right, and then this is more applicable to what we're doing with resampling. Let's say we have our array of values and we want to pick multiple samples of 5 elements each from that. So we can do numpy.random choice, pass in our X, and then the second argument is going to be a tuple. So the first value is how many elements we want in each sample. So we want 5 in each. And then the second value is how many samples we want. So here we want 10. So if we do that, we get 5 random, or wait, let's do it the opposite way. We want 10 samples of 5 each. So the first element is how many arrays you want, and the second is how many in each one. So there we have 10 with 5 elements in each. Does anybody have any questions on this stuff so far? All right, so let's move on then to the Bootstrap method. So first we're going to start with normal data. Here we're going to use what we just did, basically creating sample data from a normal distribution with this mean and this sigma, and we're going to create 1,000 data points. Now we can plot this, and we can see it looks like we'd expect. It mostly follows a normal distribution. Since we did 1,000 data points, it's not perfect. If we were to increase this, it would more and more look like a perfectly symmetrical distribution. And let's say we're interested in a value in particular. So you could call this anything, like maybe speeds of cars on a highway. So like most people drive around 50, but you notice someone going 60. So you basically want to do a hypothesis test around that and get the p-value at 60. So we'll set our x bar to 60 there. All right, so to find that p-value, you would just use the SciPy library in a normal distribution, pass in your mu and sigma, and then do the CDF at that x bar, and we would get this p-value here, so 2%. So now to do this with bootstrapping, we're basically going to choose a number of reps or repetitions. We're going to do 10,000, which is a lot. And then we're going to pick a bunch of random samples. We're going to pick 10,000 of them, and they're all going to be the same length as our original sample. So if you go back, n was equal to 1,000, we have 1,000 data points. So now we're going to have 10,000 samples that are 1,000 elements in length each. And we'll create that there. All right, so now this next part might look kind of confusing. So let's see. Let's break it down a little bit. All right, so first of all, this part here, you can use numpy.where and then pass in an array and then like a Boolean expression. So we're going to look at our, let's see. Well, this is within our list comprehension. So you can just imagine this is basically each of our samples that we created, each of the 10,000. But basically we pass each one in and we can check if all the elements are greater than our x bar of 60. And this will return a list of all of the places where that condition is met. And then it returns a list, so we have to get basically the first element of it. And then we add on the length to get the length of it. So we're basically finding how many values in each sample was greater than that threshold of 60 that we're looking at. And then lastly, we're going to divide that by the number of repetitions. And then we sum all those together and take the average. So if we run this, we can see that we actually end up with almost the same p-value as just doing it with a normal distribution. So now we're going to try it with non-parametric data. So this here is kind of a way to make a non-parametric sample of data. So I've taken basically the combination of an exponential distribution and a normal distribution, and you can see what it looks like here. So we can see we have definitely not a normal distribution. It's very skewed to the right. There's no negative values. So this would be kind of hard to deal with, just using a normal distribution like normal. And in this case, since the scale is a little different, our threshold is going to be 80. That's going to be our x bar that we're looking at and trying to find the p-value at, the tail above it there. So we do this the same way, 1 minus the stats normal distribution at the mean of the sample and the standard deviation of the sample, and then the CDF of that. And so for that, we get a fairly small p-value there. But so now, the better way to do this, since it's non-parametric data, is to use the Bootstrap method. So again, you take 10,000 samples, all the same length, and create those. And now we're using this function here again. We're basically finding all the times when we got values greater than that threshold, the X bar, and kind of taking the average of those and then finding the mean. So this actually gives us a higher p-value because if you look at the data, the tail is really long. So if you're looking at 80, you know, there's kind of a lot of possibility there after it. And so doing it with just a normal distribution probably isn't the best way because it gave us such a low p-value. So we might end up doing a type 1 error. So using the Bootstrap method, since it's nonparametric, is actually better in this case. So to kind of give you another scenario, we can also use this to calculate confidence intervals around a mean. So to do this, we're going to use the same distribution we were just working with. We're going to basically find the mean of each of our samples. And let's see. So if you look at this here, it's an array of all the means of each of our 10,000 samples. That's what passing in the axis equals 0 does. So now we can find the lower interval and the upper interval for the confidence around the mean by using this percentile function off of NumPy. We pass in our list of means, and then we tell it the basically, so this is if we wanted 95% confidence. So on both of the tails, we have 2.5%. So together, that's 5% significance or 95% confidence. So if we run this here, we can see that we get these two intervals around the mean of our sample. And actually, if you subtract the true mean, or if you look at the distance from each of these intervals to the mean, you can see that they're different. And this should stand out because normally when we find a confidence interval using the normal distribution, it's symmetric on both sides. So it should be an equal distance on each side. But since our distribution is nonparametric, we have different data on each side. So it makes sense that one of the intervals will be like pushed a little bit farther away from the mean. And I think I have a visualization of that. So here we're just going to calculate the confidence intervals around the mean in a normal way. So using SciPy again, just finding the interval 95% around the mean, passing in the standard deviation of the data. And that will give us this. And you can already see the numbers look crazy different. So now if we plot the two to compare them, so the red lines here are the confidence interval for the Bootstrap method on what the mean is. And the green lines are for if we used a normal distribution for this data. So you can see the normal distribution is way off. There's no negative values, but it's saying the mean could possibly be negative. So in this case, especially, using a normal distribution does not work, and using the Bootstrap method can give you a better estimate around the mean. All right, so now we're going to talk about Jackknife. It's similar to Bootstrap. Bootstrap honestly is probably used more often, but Jackknife is a little bit simpler, and there's some other benefits to it that you'll kind of discover here. But the basic idea that you need to understand behind Jackknife is that if our data is this array here, 1, 2, 3, 4, to jackknife it would be to make a sample for each possibility of removing one of the elements. So basically we go down the line each time we remove one of the elements, and we use the rest of the array as one of our samples. So from this small array, if we jackknifed it, we would end up with these 4 samples. So each one just has one of the other values missing. So that's kind of the basic premise of Jackknife. So now we're actually going into an activity. The first task is going to be create a function that does that Jackknife method. So it's going to take in an array, and it's going to return a list of arrays that each has one of the elements taken out. So I'd recommend to start off simple, like maybe with that 4-element array, and see if you can do it with that. And then you can try it out with like a larger size one. So then after doing that, you're going to basically copy the code that I had above to create both a normal and a non-normal sample. And then for each sample, you're going to pick some extreme value, so like a value on like one of the tails maybe, and calculate the p-value for it. And then also do the 95% confidence interval around the mean. And you're going to do this both the normal way, using a normal distribution from SciPy, and then you're also going to do it using the resampling way with your Jackknife sample. And then lastly, there's a question here, once you've done that, to compare them, basically talking about the advantages and disadvantages of Bootstrap versus Jackknife. So before we begin, does anybody have any questions? How are you guys feeling about this? Like thumbs up if you're good, maybe iffy. Iffy, I'm seeing so-so. Bonnie's in the middle. Okay, well, let's pause record.
Okay, so these two are the same function. It's just this one returns a list and this one returns a numpy array. We found that it was a lot easier to calculate stuff when we returned a numpy array as we were troubleshooting. So basically what we did is we set up this is our like list of items to go through. So we were thinking about how, like, what is the shape of the output that we're going to get if we're trying to pass in this list with one thing removed. Well, we figured that it's a permutation, and it's probably going to be something close to the, like, it's going to be equal to the length of the list. And so that's why we passed in this range. Then the next thing we did was set up a copy. And the reason why we set up a copy is because we didn't want to change the original list as we're iterating through it and ultimately removing one of the variables. And so the way that we removed it was by referencing the copy. And then we reference the original list with the counter. And then we put that into a list and returned it. And so our output for the Jackknife, the short version looks like this. This is the long version. And then this is the stuff that happened after. Do you want me to explain this too?
We'll just go ahead and show the other Jackknife first, and then we'll come back to that stuff.
Okay.
All right, so then for comparison, Juliet, what did you guys do for Jackknife?
Let me share. Okay. So this is it. We had our list for the results that we were going to have at the end, and we did a for loop for the range of the length of the list. Then we need to have another list so that we could add what we were going to put. Oh, I didn't show like an example. Sorry. So that we could see what, so we could add to that list again. So we enumerated through it with an index and our value of what we were going to get inside of that list. And if that index from our original part was not the same, we could just add that value to our list, and then our list would come out. So if we did Jackknife, did that make sense? What I said there? So let's say we did 1, 2, 3, 4, and then we passed in X. That's what we got. So went through each one, and then as long as they were not the same, the index with the original index, it would add it to our results list. Yeah.
All right, cool. So now I have a question for you guys. So comparing those two methods, which do you think would be more efficient and take less time if you passed in a really, really long array? So if you think about the structure of them, Beth's had just one for loop and it just made a copy each time, whereas Juliet's had two nested for loops.
The first one.
And why is that?
Because of the amount of iterations that you have to go through. On the second one, it's for every number of elements in the array, you have to do X number of times. So it's like an exponential, right? X times X. And in the second one, it's just one copy, and you do once the number of items in the array.
Right, that's exactly it. So basically the nested for loop will increase in an exponential way in relation to the other one as you add an element to the array. This is basically big O notation. It's something that you see more in software development. But basically the first function with one for loop would be what they call O of n time or complexity. And then Juliet's with the nested would be O of n squared, because as the number increases, the time increases by a squared fashion. So, okay, so now let's talk about what we discovered using the Jackknife function. So if we want to go to either Beth or Bonnie to show what you guys got.
Bonnie, I think yours is laid out a little bit better than mine. And I don't think that I saw what we were supposed to see with mine.
You're on mute. We can't hear you. Funny.
Okay, can you see it now? So we basically first create a normal distribution using n equals 1,000 and mean with 100 and sigma, standard deviation of 5. And this is the shape of this normal distribution. And I select the bar being 1 and 10 and calculate the p-value is 0.02. So using the stats formula, the 95% interval is this. So then we use Jackknife sampling method. We use the same X from that normal distribution, and we turn it into a list and get this sample. So this is the first, because it's an array of arrays. So I just select the first sample as an example and plot this one. This is not the correct plot. This is the correct plot. And we use the Jackknife mean here and to use a 95% confidence. And we get this confidence interval. Get this interval. And this is our p-value, which is very close to the p-value we get from normal distribution. Yeah.
All right, cool. Thank you. So now, Jacob, you want to show what you guys got? We can kind of compare.
Jacob, you could talk, but I'll share my screen. If Jacob is there. Is he there? No?
Jacob's computer crashed, didn't it?
Okay, so what we did, we actually did a smaller sample because when we did it with the bigger one, Jacob's computer like stopped, so we made it smaller just in case. So our sample was 100 and then we got a distribution. We're doing the normal one, right, Matt?
Yeah,
Oh.
you could start with the normal.
Okay, so this was it, and then we chose a value of 55, and then we got a p-value of 0.15. So then we had to take, using the Jackknife, right, we had to make it into an array so that we could get the means, and this is our means. From there, we needed to find the confidence, right? The confidence interval for 95, and this is what we got for that. And then comparing it to the normal distribution using the graph, we saw what it would look like between the red is the Jackknife and then the green is our normal distribution. So we compared them like that to see what it might have looked like.
So are there any benefits there over the Jackknife versus the normal distribution?
Well, in this case, it looks like they're pretty similar, but the Jackknife does show better inside of the distribution, but they kind of look similar.
So the second one, you use the means of your samples, right?
Yes.
Should we use that, Matt? Because I did not use the mean of my samples.
Yeah, so for the interval, it's around the mean. So you basically are finding the means of all of your samples.
But my normal distribution is just the raw data is not the distribution of means, right?
Right.
So if we're comparing the normal distribution, which is raw data, with like distribution of means, is there a fair comparison?
Yeah, so what you're doing is basically finding the confidence interval the normal way, like by saying that your sample comes from a normal distribution, and that gives you that interval. And then doing it the Jackknife way, you're taking all of your samples, finding those means, and kind of pairing them and using them to find the confidence interval. It's doing like a similar thing, but with the normal distribution way, you're assuming that your sample comes from a normal distribution. So it's just using that curve specifically. But the Jackknife is only using like the actual data you got in your resampling.
Mm.
And actually, Juliet, if you can show your graph one more time.
So is it because if it is a normal distribution, we can do this comparison? If it's not normal, we can just compare the raw data with the sample means, right?
Yeah, so it makes more sense to compare it with the normal distribution because that's what we usually use like the normal distribution methods for, like finding the confidence interval in this way. But when we have like a skewed data set or something, then, you know, in real life, you won't actually use a normal distribution to kind of model it. You'll use some kind of non-parametric means like the Bootstrap or the Jackknife. And this kind of shows it here. So they took 100 samples from a normal distribution, but you can see that it's slightly skewed to the right since it was just 100 samples. So the Jackknife, the red lines actually accommodated for that and more closely fit towards that right skew. You can see that the distance from the black line to the right red line is a little bit further. Whereas for the normal distribution, it just put the lines down on opposite side, like equidistant from it. And it didn't really take into account the skew of the data. Does that make sense?
Yeah. Matt, will you share the solution of this?
Yeah, I will. I'll post it here either tonight or tomorrow.
Okay, thank you so much.
Yep. All right, and then just to bring it home, do you guys have any ideas of why you might use Bootstrap over Jackknife, or kind of some disadvantages or advantages of them?
So I know that I can see, coming from a medical background, how Jackknife will be really valuable, because it's not like I can just go inject 15,000 people, right? And so to really get a picture of what the data is doing, I can see this resampling technique being really valuable whenever you have a smaller sample size. So let's say I applied for a grant where I would be able to test 30 people or 300 people. No, let's do 3,000 people, but I only got the funding to test 300. So I could do this resampling technique to get my data to that 3,000, because let's say I needed 3,000 to actually get the power right, if that makes sense. Like I needed that sample size. I could use this resampling technique to acquire that sample size, even though I didn't actually test that many people. Whereas compared to the Bootstrap, I can see Bootstrap being really helpful whenever the data doesn't do what you expect it to do. So let's say I'm developing this drug, right? And I expect it to have this certain reaction rate. And I expect that reaction rate to be linear, but instead it's logarithmic or exponential, which would give us this non-parametric look to our data. I can see the Bootstrap being really helpful to kind of understand what's happening so that I can develop another study to get that linear regression that I'm looking for.
Yep, so in general, the resampling methods are basically really good when you have low sample size or when your data isn't normally distributed. So if it's really skewed to one side or whatever, it's good in both of those cases. But just for the comparison of like the Bootstrap versus the Jackknife is actually an older technique. It was kind of the first kind of resampling method. One thing about it is that it's like less computationally expensive. It's like a limited number of samples you're going to generate. Another thing is that you always get the same samples each time. So it's really easy to reproduce your results. Whereas with Bootstrap, it's all random. That being said, you can set the random seed now and kind of recreate random results that way. So it kind of lost that advantage for it. But yeah, they do have some other differences in terms of like Jackknife's better for dealing with outliers, because it'll go through, and if you have like one really big outlier, it will have one sample with that outlier removed, so you can kind of better compare the data in that way. And there's some other differences that are a little more complicated, but that's the basics of it. Does anyone have any questions on anything covered tonight? How are you guys feeling about like this topic in general? Good? Okay. As long as you're at least like, okay, that's good. All right,
Yeah.
awesome.
In interviews, I was asked like how to deal with non-parametric samples and do hypothesis testing. So this like Jackknife and like how we can use non-parametric intervals really helpful.
Cool. And you'll get to do a lot more practice here with the Mod 3 project, which brings me to the next topic. It'll probably be deployed tomorrow, so it'll be available for you guys to start looking at, digging into, whatever you want. But also tomorrow night, we're gonna have a study group. We're gonna talk a little bit more about non-parametric tests just for like maybe 10 minutes to introduce you to those. And then we're just going to start on the Mod 3 project. So the goal is to kind of get the first little section knocked out or get you guys like up and running immediately. So if you can make it, it'd be cool. If not, we'll record it and you can definitely follow along to kind of catch up.
Cool.
Yep.
Thank you.
You're welcome. Thanks, everyone.
Bye.
Bye.